So welcome to the final unit of the topic around reaction kinetics, activation energy. So by the end of the unit you should be able to apply something called the Arrhenius equation. Realize the graph of 1 over t against the natural log of k is a linear plot, and what its intercept actually means along with what its gradient can be used to interpret. Know what the frequency factor is. And then also be able to analyze graphs involving the Arrhenius equation, use the Arrhenius equation, and describe the relationship between temperature and the rate constant, the frequency factor, and the complexity of molecules colliding. And finally, determining and evaluating values of activation energy and the frequency factors from data. So just some revision of the logs. Okay, so b equals a to the power of c, then c log of ab will be b to the base a as c. For example, 8 equals 2 to the power of 3. Most common logs are base 10, which is log base 10 there. Natural log is base e, or 2.718. Okay, so with that in mind, let us continue on. So essentially the lesson will be based around the Arrhenius equation, and the chemist Svante Arrhenius developed a mathematical relationship between the rate constant and activation energy, which is K equals A e to the negative EA over RT, where A is the frequency factor, also known as the Arrhenius constant, which is the number which defines the likelihood that collisions will occur with a proper orientation for the reaction. Okay, so basically a probability. The activation energy is EA, and temperature is in Kelvin. And R is, of course, the universal thermodynamic Gauss constant as given, which is also in your data booklet. So you can use an Arrhenius plot. Okay, so if you plot the natural log of the rate constant against 1 over the temperature, you will then discover by taking the natural log of both sides that you'll get a y equals mx plus b relationship, where b is going to be a determination of this Arrhenius constant, and the gradient will be a reflection of the activation energy. Okay, so when k is determined experimentally, which it has to be done, as we learned in the last topic, at a range of temperatures, the activation energy can be calculated from the slope of a plot of the natural log of k versus 1 over the temperature, of course with the temperature being in Kelvin. So how do you determine the activation energy? Well, you have to convert the rate constants k into natural logs. You take the natural log of all the values of the rate constant, convert the temperatures to Kelvin by adding 273 if it's in degrees Celsius, and then taking the reciprocal, and then you plot natural log of k versus 1 over the temperature. By measuring, or calculating, we're not really measuring, calculating the gradient of the line, this will give you negative the activation energy divided by R, and since we know what the value of R is from the data booklet, you can solve that equation to find the activation energy. So for most equations, an increase of 10 degrees Celsius, or I guess 10 Kelvin, will double the rate of the reaction. Okay, so here's a problem. So what you need to do is use the graphical method to determine the activation energy for this particular reaction. So there are the experimental values. You need to plot them on a graph and then use the graphical method to determine the activation energy. Once you have done that, play the video and see if you get the correct value for the activation energy. Good luck. Right, so the first thing you have to do is probably create a second table of the reciprocal temperature, of course in Kelvin, and natural log of k. So you should have got these particular values. Once you plotted it, the gradient you should have got would have been around about negative 1.233 times 10 to the 4 Kelvin. Okay, so we're nearly there. Okay, so you should have got a gradient of about negative 1.233 times 10 to the 4 Kelvin. which will represent essentially negative reactivation energy divided by R. Okay, so that means that activation energy equals R times 1.233 times 10 to the 4, which equals 8.31 joules per Kelvin per mole times 1.233 times 10 to the 4 Kelvin. So if you solve it for activation energy, you should get a value of 102,462 joules per mole, or 102 kilojoules per mole. So hopefully you got that correct, and that is pretty much all you need to know for kinetics for both SL and HLIB. The next topic will be equilibrium.